we are going to talk about storage and other IO topics, right? So chapter 6, which is about storage and input-output. So in the introduction, let us have a look at the input-output devices and storage devices associated with processors, right, in computer systems. So IO devices can be characterized by behavior, partner, and the data rate, right? So we can consider the behavior as input, output, or storage. Partner, human or machine. That is, the device is communicating with another, which could be a human or machine. And the data rate, bytes per second or transfers per second. So in the IO bus connections, a simplified version is given here. You have a processor, you have a cache, and you have a bus which we consider as the memory IO interconnect. Then the processor and the cache both are connected to the bus, the interconnect, right? So if you look at the processor is getting more than one connection, which we consider as interrupt from the bus, right? That is basically from the devices. So on the other side of the bus, we find main memory, IO controller, 3 IO controllers, one IO controller connected to the disk. So we have IO controller connected to the graphic output, and we have another IO controller connected to the network channel, right? So we are talking about the IO system's characteristics. Dependability is important. We use the processor for data manipulation. When it comes to processor usage, we need to consider the input-output. So an input-output system has to be dependable, right? Dependability is important, particularly for storage devices. You're storing something that should be reliable, right? So that is the dependable. You are depending on that. How much you can depend on that, right? Performance measures. When you think about an IO system, you will consider the performance measures. The different measurements are there for performance, latency, throughput. We have already talked about them. And when you think about embedded systems, we are interested in response time, and the response time is that is expectation of the response time is not same because of the diversity of the devices. Okay, because of the diversity of the devices, the response time which we expect will vary. And servers. In servers, we are mainly interested in throughput and expandability of devices. You know what is a server? It is about throughput and expandability. Okay. Dependability in detail. We have two states of a device. One is service accomplishment, the other one is service interruption. Service accomplishment means service delivered as specified. Service interruption is deviation from specified service. If you are in service accomplishment state, if the device is in that state, due to a failure, it will transit to service interruption state. And from service interruption state, after restoration, it will go to service accomplishment state. So the term fault is defined as failure of a component. Faulty system. When we say fault, it is failure of a component, due to failure of a component. It may or may not affect the system. That is why they say it may or may not lead to a system failure. Having a fault component, still the system can be up and running. Then it could lead to correct output or wrong output. We don't know. And dependability measures. There are some measurements. We have this term reliability. Reliability is measured as mean time to failure, MTTF. And we have another term, service interruption. When the device is in the state of service interruption, we have a term mean time to repair. How long it can be in that state, right? For a particular device, possibility. So, mean time to repair. Then we have this mean time between failures. So, mean time to failure, mean time to repair. Both together we say mean time between failures. You have one failure, you repair it and it will be reliable for some time, then again it fails. So we add the two values and we say MTBF. And we have availability. Availability is defined as MTTF upon MTTF plus MTTR. Okay. That is the availability. Proportion of time. The machine will be available. And improving availability. How? Improving availability, we need to increase MTTF. Mean time to failure. That is the time the system will be available. How can you achieve fault avoidance, fault tolerance, fault forecasting? Okay, fault avoidance you can do, fault tolerance you can do, fault forecasting you can use. So you can forecast the fault, prediction. Tolerance means you have to find a mechanism to withstand the fault. And avoidance. Before the fault arises, how can you avoid it? So these are the mechanisms we can use to increase the MTTF. And reduce the MTTR. So we are interested to reduce the mean time to repair. Make it fast to recover. Improve tools and processes for diagnosis and repair. Okay. And the example, we have it in the book and you can try. So we have some values for MTTF and MTTR and based on that, we have some questions, right? So please try them. And storage. Disk storage. So you know that when we talked about memory, we said that we have a hierarchy of storage. So hard disk is in the lower level, cache is in the upper level, right? And when we talk about hard disk, it is non-volatile. We say permanent storage because it lasts for long. And the material we are using to store is rotating magnetic disk, right? Magnetic storage. And disk sectors and access. We are not going into very deep, but to get some knowledge about how the disk will be accessed, we talk about sectors and access. So if you take a hard disk, it is a round shaped one, right? Circle shape. So in that, how can I say, towards the center, right? From periphery, that is outside the edge of the disk, towards the center of the disk, we have number of tracks. Okay? Some of you may be familiar. Tracks mean you can imagine like we have multiple small ribbons, right? Arranged one after the other from the periphery to the center, right? So those are called as track, like the track people used to run in games, right? In Olympics and all, we find large tracks, right? And these tracks are divided from center to the periphery. We make a cut, cross section, right? Cut a cross section, and though we have a number of separation like that. So the portion between two separated lines, we name as sectors, right? That is how it is named. So each sector records sector ID and the data size, that is how much you can store in a sector, can be 512 bytes to 4096 bytes. And we will also store the error correcting code used to hide defects and recording errors. And there may be gaps in the sectors because there could be some unused spaces, gaps, right? So access to a sector involves queuing delay if other accesses are pending. So who is accessing? The processor, memory management unit will do the accessing to the disk. So that involves the contribution from hardware and operating system. So we already discussed, reading a page from hard disk to the main memory will consume millions of cycles. In that case, there could be pending request, pending accesses. So there might be a queue for disk access. And we use the term seek. So you must be aware that we have this a head, right? A head pointing or touching the disk, right? To read. We use the head to read. So this head, the physical part of the hard disk, will move around, right? Actually, the hard disk rotates. So we say move the heads, right? So to position the head in the right sector, because it's a round circle shaped disk, so it has to be rotated to position the head, which need to be placed on the right sector, right? So the head is placed diagonally on the disk. Hope you can understand. So that time is known as seek time, seeking the sector. And rotational latency, right? So as I mentioned, that to find the sector, we need to rotate. So the rotating latency. Because if you take a sector, I told we make a cross-section cutting. So that is diagonally we separate them. So in that case, we will have a number of sectors in each track. So we need to position it accordingly. So rotating the disk, we say rotational latency. So the disk is 360-degree one. Can be moved either way. So we can choose the closest move, the quick move, which side you can quickly reach the corresponding sector. Right? These are the details about how we move the disk. And the next, the time for data transfer. And controller overhead. There is a controller handling all these things, the data access. So we have a controller overhead. So we have an example for disk access. We have the sector size 512 bytes. We have the rotational speed RPM 15,000 rotations per minute, right? And then next we have 4 millisecond seek time. Position the head on the sector. Then 100 MBs per second transfer rate. 0.2 millisecond control overhead. We assume an idling disk. Okay. So the average read time is derived as 4 millisecond seek time plus half 15,000 divided by 60. Because it is given in minutes, we need to compute into seconds. And why we say half, the disk can be rotated either. So half, we choose the closest path. So we have a 2 millisecond rotational latency. Okay. So rotating the disk and choosing the right sector. Right. And 512 upon 100, because the speed of data transfer is 100 MBs per second, we are transferring one sector, which is 512 bytes in size. So our transfer time 0.005 millisecond. Controller delay 0.2 millisecond. Altogether we get 6.2 millisecond. If actual average seek time is 1 millisecond, average read time is 3.2 millisecond. Although the company says 4 millisecond average seek time, depends on which sector and where the head is currently located. The distance between the two, right? So if the seek time reduces to 1 millisecond in the real case for a particular access, your access average read time will be reduced. And another example is given here. So you may try that. Flash storage. It's a very popular one. We all are using them. So these slide sets are little bit older. So the values given here might be varying for the current flash storage devices. So they are non-volatile semiconductor storage. They are 1,000 times faster than a disk. Smaller, lower power consumption, more robust. You know, like the flash storage, we can take around. So it's more robust. But it's expensive, right? Because of the technology used for the storage. So the types of flashes briefly given. NOR flash. NOR flash, the bit cell like a NOR gate. Random read-write access. So this could be randomly read and written. Used for instruction memory in embedded systems. Okay, used for instruction memory in embedded systems. NAND flash, bit cell like a NAND gate. You know, bit cell is the cell used to store a bit, right? Bit cell. Denser, but block at a time access. So the difference between the NOR and NAND is you can access bytes in case of NOR, whereas you can access blocks in case of NAND. So the reading and writing is done as blocks, block at a time, right? Cheaper because of the technology, used for USB keys, media storage, etc. Okay. So we have memory mapped I/O. Registers are addressed the same space as the memory. Address decoder distinguish between them. OS uses address translation mechanism to make them only accessible to kernel. Okay, memory mapped I/O. So we reserve some addresses for I/O. If you have 8 lines, you have the possibility of addressing 256. Maybe you will have only 128 locations reserved for memory, and you can leave the 128 for I/O. I/O instructions. So in the previous case, we can use load store instructions to access the I/O devices. In the second mechanism, we will have separate instructions to access I/O devices. That is, the load store will be used to access the memory, and the input-output instructions will be used to access the I/O. So here we can duplicate the address. You can have the same address for memory, and the same can be used for, a single address can be used for memory and also in an I/O device. Separate instructions to access I/O registers can only be executed in kernel mode. The example is x86. Polling. Periodically check I/O status register. Periodically check I/O status register. If device is ready, do operation. If error, take action. So the processor will keep on checking a device to communicate, and it will make decision based on that. It's common in smaller, low performance real-time embedded systems. Predictable timing. We know at this time the device will be free. The program can be written accordingly, and the program can be run. We can run the program to read a bit from the device and check whether it is free or not. So low hardware cost because the software will take care of the communication. In other systems, if you try to run a program to check a device, it will be looping and the CPU time will be wasted. Therefore, we go for the mechanism interrupts. Here, the device has to initialize the communication. It will send a signal request to the processor asking for the service. So it is happening when a device is ready or an error occurs. The controller will interrupt the CPU. Interrupt is like an exception, but not synchronized to instruction execution. You can invoke handler between instructions. So that is, if you are running a program, when one instruction is completed in completing the execution, you can attend the interrupt from a device, and then you can follow the next instruction in the main program. Pause information often identifies the interrupting device. And the priority interrupts. All devices are not having the same urgency. So based on the urgency of the devices, we have categorized them into different priority levels. Devices needing more urgent attention get higher priority. I/O data transfer. Polling and interrupt-driven I/O. CPU transfers data between memory and I/O data registers. Time consuming for high-speed devices. Direct memory access. Direct memory access is we let the DMA controller, a controller we name as DMA, direct memory access device, to do the transfer between the memory and the IO device. So this removes the intervention of the processor. The processor will hand over the transfer job to the DMA controller. It will take either way it could be done, to the device or from the device. Memory to device or device to memory, anyway. So OS provides starting address in the memory. IO controller transfers to one from memory autonomously. Controller interrupts on completion of error. In conclusion, IO performance measures throughput, response time, dependability and cost are also important. Buses used to connect CPU, memory and IO controllers. So we can use polling, interrupts and DMA mechanisms, and RAID improves performance and dependability. So there are some exercises you may do that.